Okay, before continuing with chapter 3 of structure and interpretation of computer programs, I would like to do a brief recap of what we have seen in chapter 2. Um, so, the central idea is that programs, computer programs, should be built around abstractions and not representations. And chapter 2 introduces data abstraction, the idea that when we define new kind of data object, we should strictly separate what the object means, so its logical identity, and how the object is implemented, that is, its physical representation. And this separation creates an abstraction barrier, and so basically the code above the barrier uses the interface, and the code below the barrier owns the representation. Neither side needs to know about the other. And if you think about that, this is the foundation of modern software engineering. And it's incredible that it was articulated in a book written in 1984, so decades before microservices, APIs, or interface driven design. Another important concept is that the interface is stable, while the implementation is free. Take rational numbers, for example, and we define a constructor and two selectors. That is the entire interface. Users of makeret, numer, denom need not know whether the pair is reduced, normalized, or stored as a vector or as a pair. Sorry. The internal representation can change freely as long the interface holds. So once abstractions are stable, systems become composable. And composition is what software engineering is fundamentally about. Another important concept is that a pair, which is the basic structure of Lisp, of Scheme, is not really or is not only a memory structure, but it is a function. And at one point, structure and implementation of computer programs shows that pairs, the fundamental data structure, can be represented using nothing but procedures. So no objects, no memory, just closures. And this is philosophically very interesting because it means that data and behavior are not rigidly separate, that a programming language is a system of representations, and that abstraction matters more than physical structure. I think we should read again these 3 points. Data and behavior are not rigidly separate. A programming language is a system of representations, and abstraction matters more than physical structure. And this idea anticipates closures, message passing, object systems, and basically much of modern programming theory. Another key point, another key takeaway from chapter 2 are programs that reason about representations. Indeed, chapter 2 introduces symbolic data, so programs that manipulate not numbers but expressions, variables, and algebraic structures. And this symbolic differentiation examples are extraordinary. Basically, instead of computing a derivative by hand, the program works an expression as data and transforms it by rule. And the key shift the key shift is that programs can reason about programs, that code and data become interchangeable, and the computer becomes a system for manipulating knowledge. And yes, and probably this is why Lisp gave birth to symbolic AI, compilers, theorem provers, and metaprogramming. And the boundary between code and data was always meant to collapse. Another takeaway, recursive data mirrors recursive processes. And chapter 2 extends recursion from processes into data itself. Lists inside lists, trees, structures that describe themselves. And you start seeing that recursive thinking is not only a technique for computation, but it is a natural way to represent complexity. And we saw that also in chapter 1. And if you think about these mirrors reality surprisingly well. Think about file systems, syntax trees, organizations, biological systems. All these or complex systems are hierarchical. And I think that once you understand trees, but in general hierarchical structure deeply, parsers, compilers, databases, and graph algorithms all become easier to reason about. Another key point is multiple representations, one coherent system. So there is a question, a central question: how can a system support multiple internal representations transparently? And the book asks this question using complex numbers, representable in rectangular form or polar form, and each useful for different and useful and convenient for different operations. And the answer to this question introduces several powerful ideas. The first one is type tags, so the idea that you can attach a label to data so the system knows what it is. The second is data-directed programming, so that is basically dispatch on type to the right operation. And the third is, which is only mentioned in the book, while the other two are presented through examples and are discussed extensively. The third one is message passing, so basically treating objects as bundles of behavior. And if you reflect on these three ideas, you see that these are the conceptual foundations that lie behind polymorphism, interfaces, protocol dispatch, and dependency inversion in modern software engineering. And so to summarize, this chapter 2 of Structure and Interpretation of Computer Programs, does not teach the data structures, but it teaches a philosophy of representation. Think about the same idea can have multiple representations. Representations are arbitrary and only the interface persists because in the end users use the interface and not the logical representation that stay behind the interface. Abstraction barriers protect complexity at scale, Symbolic manipulation enables reasoning about knowledge, and interfaces matter more than implementation details. And if you make if you internalize these five concepts, you stop seeing programming as a writing instruction for a machine, and instead you start seeing programming as designing systems of thought, designing systems of knowledge. And to conclude, the biggest takeaway is that intelligence, software engineering, programming, computer science, language are all connected through representation. And the boundary between code and data was always meant to dissolve. And as I told you before, once you internalize this idea, you never look at programming the same way again. And I think that this is the real power of this book, because leave aside all the examples that are grounded on algebra and mathematics, number theory, etc. This book, by means of these examples, illustrates ideas that are so powerful, so foundational, that once you internalize them, you start seeing programming in a different way. I think that's the reason why this book became so popular in the years. So, a brief summary with 7 ideas from chapter 2, and then we are done and we can continue with chapter 3. The first idea is data abstraction, so separate what an object means from how it is implemented. Abstraction barriers, so stable interfaces decouple users from representations. Third idea, data is equal to procedures, so pairs can be closures and the boundary between data and behavior is not fundamental. Fourth, symbolic manipulation, programs can reason about representation, and this is the root of metaprogramming and AI. Fifth, hierarchical structures, so recursive data mirrors recursive processes, and trees describe complexity naturally. Sixth, generic operations by means of type tags and dispatch that let multiple representations coexist transparently. And seventh, representation as a philosophy. So programming is not about machines, but is about designing systems of thought. And with these 7 ideas, we can conclude chapter 2, and we'll see you. I'll see you in the next video on chapter 3. Bye bye.